All right, last section we were looking at testing the hypothesis for a sample mean. So now we're going to look at what if I have two samples, so that I'm no longer comparing a sample to the population, but I'm comparing a sample to another sample. And maybe it's that I go take a sample and you go take a sample and they're totally independent, but let's say they're from different regions. So, maybe we're testing a theory that people are more likely to like Dr. Pepper in Texas than in New York, which they probably are. So maybe you're taking a sample like that and then you're going to compare the sample means of their rating of Dr. Pepper. So that is an independent samples t-test. Two sample t-test. Independent because the two samples are independent of each other. But if you're going to compare instead, let's say how much someone likes Dr. Pepper as a child and then how much that the same people, the same sample, like each other, not each other, like Dr. Pepper as adults, then that comparison is not independent because it's the same people. You might also instead say the rating that husbands give it versus wives. So this is now a married, couple, so they're paired. There's a natural way to pair the two people and that it makes sense that they'd coincide. If you love Dr. Pepper as a child, you're more likely to love Dr. Pepper as an adult, but maybe adults generally like it less. If you're married to someone, you have a tendency then to, end up eating and drinking the same things a lot of the time, so that may make you more likely to like Dr. Pepper. But I know of couples where one of them's Dr. Pepper and one of them's Coke. So it's that kind of thing is called a dependent two sample t-test because there is a connection between the two samples. We look at them differently because on the first one, we're comparing these two samples as wholes. So we're looking at the average of one and the average of the other and seeing if that's different. But on the dependent samples, we'll be comparing husband to wife or child to same grown person, like that, so that it's a partnered thing. Okay, so let me just show you the formulas for the one that's more complicated. The independent one is the one that's more complicated. So what we've done before for samples for the standard error is we just take the standard deviation and we divide by one fewer than we had in the sample. So we can't do this now because we have two samples. They don't have a single standard deviation. So what we do is the standard deviation of one of them squared divided by how many there were, and the standard deviation of the second one squared divided by how many there were, and then we take the root of that. So normally the root would be over the ends, right? So there should be a root present, and to kind of cancel out the action of this root, we're squaring these. It doesn't exactly cancel it out. This may look a bit like the distance formula to you because it's related. So this is a thing that is commonly done in mathematics, is that we square a bunch of things and add them up and then take the root, and that gives us a kind of general size. So distance is a general size. When you do the distance formula, this one's x and this one's y, and it tells you how far away am I total when I've gone x in this direction and y in the other. So this is a very similar notion that we have happening here. Okay, so that's how you'll plug that in. And then the degrees of freedom is actually a kind of nightmare. So if you look at this, you've got this stuff that you did under here, but now instead of a root, we're squaring it. And then over here, you do the 1 over 1 fewer times the standard deviation squared over n all squared. And then the same for the other. So this is horrible. So while this one is more accurate, we can do one where we basically do an overly safe version of this thing. So now instead of This formula will just use whichever is the lower of the two ends, we'll subtract one, and then we're building in way more padding. So if we end up saying we're rejecting the null hypothesis, boy oh boy do we have a right to do that, because we've been really, really conservative in our approach to this thing. Okay, so this is what you need for the independent one. It was random in both cases. The random samples are independent of themselves and of each other. And the population distribution is normal in both populations, or you have a huge sample. So we've talked about this before. If you started out with a normal sample, then you didn't have to have that many people, really. It was like 15 or 16, right? But then once you get past 30, it doesn't matter if the distribution of the population was normal. The distribution of the sample means was. So this is going back to the previous unit, basically. Okay, so here's an example of an independent. This is, so there are two different teachers. They're comparing two different teachers' scores. They're given a standardized test. So they're tested on the same thing. And they want to know if the two classes perform similarly, essentially. So here's one population is class 1, and they take a sample. In class 2, they take a sample. They're not the same size. They calculated the mean, they calculated the SD in both cases. There seems to be a huge difference in the mean. The null hypothesis is that we expect them to be the same. We expect mu1 to equal mu2. Then the alternative hypothesis is that it's not, right? It's just not equal. And of course, the UT people, anyway, prefer this always using a two-tailed. Okay, so we want to get the significance level. I don't know if it was ever given. So we'll use 0.05 because we weren't given anything else. Okay, so here's the standard error. They've got the standard deviation from the first guy and the standard deviation from the second guy. And this one had 1, 2, 3, 4, 5, 6, 7, 8, 9, and so this one had 8. So they square the first one, divide by 9, square the second one, divide by 8. Take the root. They get 5.557. Now, we're looking at mu1 is not equal to mu2. So the thing that we do instead is look at mu1 minus mu2, and then we expect that to be 0. You can see that if these are equal, then you subtract them and it's 0. So we're looking at the difference. So that's why it's this, the standard error for this difference. So the real difference was, oh gosh, 19.44. So this would be negative 19.44. And then it's minus 0 because you expect the difference to be nothing. And then you divide by the standard error and you get a t-score. So this is just exactly like we've always done before. The only thing is that you're taking the difference of the means instead of a specific mean. And you're always going to have 0 unless you're asking a different question. Or unless there's some reason, like it says instead, you know, we want to know if the difference in the means is actually more than 5 or something like that. Generally speaking, we're assuming the means are the same, so the difference is 0, so that's always going to be 0. And then the standard error of the difference of the two. Okay, so we get negative 3.498. At this point, you'd say probably that you don't even care what degrees of freedom was because this is like way far. But we would look, our smallest group has 8 students, so the degrees of freedom in our kind of cheap and easy, dirty way is 7. And then the critical value, when you look at that T-chart, would be the 2.365. To have a two-tailed with 0.05, let me pause this and go get a T-chart. Okay, so I have a t-table, and we had 0.05, but we were splitting it into 2, right? Because we're doing a two-tailed test. It's just not equal. It's not greater or less. So instead of 0.05, we look at 0.025. That's just half, 2 tails. And then we go to degrees of freedom 7, and that's where we get this, 2.365. But remember, this always just shows upper tail. So if we're looking at less than, we'd use the negative version. If we're looking at not equal to, we do plus or minus. So plus or minus 2.365. That's where this comes from. Clearly, this is beyond negative 2.365. So we reject the null hypothesis. So we say, in fact, the other class really is higher than the first class. Okay, so suppose it's a dependent sample instead. Well, let me pause. I have so many things here. Nope, that's not what I want. I want there we go. I took I took all the exam 1 Scantron scores from this 2014 test. And I chose a random sample by doing rand between on this. I assume, you know, if you do rand between, then in this case I did 1 to 72, or 73 maybe. And I did this multiple times. So if you do this, you get random numbers, and they may repeat. But then actually, if you change almost anything, it'll do it again. But I can keep doing it like that. So I did that, and I went until I had selected 20 people. And it just happens now that I've got 8 males and 12 females, even though I have, I think, more males in the grade level than females. This is just how it happened. So I split it into male and female. Okay, so then what I've done over here is I've listed the male grades, I've listed the female grades. I went ahead and calculated their mean and their standard deviation. Okay, so frequently you'll be given this. You have the formula to do it, you know, if not, but I've done it for you here, and I went ahead and gave you n, and the only reason I gave you that is because 12 of them means you land on 13, because you've got this heading row, and a lot of times that messes people up. So I just went ahead and put n down here so that there's no confusion. So what we want to do is find out, are they different? So it's the mean of the females is higher than the mean of the males. The SD is gigantic in both cases, so you know it's probably not going to be a significant difference, but this is the way we run the test, and we'll just assume alpha 0.05 also. So if alpha is 0.05, it was what, 2.365? Yeah. So we'll do T is 2.365. Now, the reason that's still 2.365, note, is because my smallest group is still 8. Okay, so this is T critical. I don't know how to make a subscript here. I'll figure that out. T critical. Okay, because I still have this 7 is still my degrees of freedom. So I don't even have to look at the chart again. Okay, so we've got standard error. And the way we would calculate the standard error, let me go write it down for you. Standard error is going to be square root of standard deviation 1 squared over n1 plus standard deviation 2 squared over n2. So standard deviation 1 is 23.1. And there were 8 of them. And standard deviation 2 was 18.6. and there were 12 of them. So this is approximately, so now I'm going to just put it into here because I'm already in here, square root of 23.1 squared divided by, squared divided by 8 plus 18.6 squared divided by 12 and I put that accidentally on the same line. Okay, so there's my standard error, 9.774. So T for us is going to be x1 bar minus x2 bar, so the difference, minus the expected over the standard error. So that's going to be, in our case, 43.1 minus 45.6 minus 0, we expect it to not be different, divided by the standard error, which was 9.774. So this is minus 2.5 so that's negative 0.256. So that's actually a very, very small difference. And that is compared with plus or minus 2.365. It's certainly closer to 0 than that. So remember what that looks like is, here's a curve. I've got these little tails that are the bad regions, reject regions, and this is 2.365. And this one's negative 2.365. And then I'm over here at negative 0.25 something. Okay, so I'm like way, way close to 0 relative to these standard deviations. So this is how you do this one. When looking at things which are dependent instead, okay, I took a little pause to save my video there. The dependent samples, they're kind of a little bit easier as far as getting your head wrapped around them based on what you already know. So this is essentially the same. Delta stands for difference. You've seen capital delta be change in, so this is the same, just delta is difference. So we expect the difference to be 0, and the alternative hypothesis is that it isn't. So this is the exact same thing. x1 bar minus x2 bar, mu1 minus mu2, these are differences, so we're just labeling the difference, same deal. Okay, so the only difference here is that, sorry about that. The difference here is that we do the standard deviation in this totally normal way. If I replaced this with x I and x bar, this would just be the standard deviation. It's the exact same guy. It's just that you're looking at the list of differences and then taking the standard deviation of the list of differences. So you don't have that standard deviation of the 1 squared over n1 like that. For one thing, you have the same n, right? So you wouldn't have to do that. But anyway, you look at the list of differences and then you kind of forget the rest, okay? So the degrees of freedom, we can go back to the normal thing because now we have pairs, right? So n, again, is the same. So we're just going to look at the list of differences, take the SD of that. Because it's still a mean, we're going to divide by root n. So this is going to be basically just like what we did before. It's just that we have to find differences first. The sample of differences is random. The paired observations are independent of one another. the distribution of population differences is nearly normal, or you have enough people. So they're going to look at now, a teacher gives a simple skills test before a class and after a class, and she's looking at then did their scores go up. The reason that the differences are all positive is not because you actually just say, oh, the difference between them is blah, and take the absolute value. It's because they actually all did go up. So each of these is positive or 0 because they went up. So we do not take the absolute values. The null hypothesis is going to be that delta is 0. The alternative hypothesis, delta is not 0. Okay, so we'll use 0.05. And so here's what they did. And of course you can read this. So let me go back now to this. So what I did now is I took exam 1, exam 2 combos. So these are the same person as far as the Scantron portion only. I again randomized. So basically I took the spreadsheet, I deleted everybody who didn't take exam 2, and then I did the rand between again to choose people. So I don't know if these are males or females, but these are pairs that go together. We don't need these means at all. The reason that I gave you these means is, one, because you would normally, if we were in a normal class situation, you would normally look at this and say, something's wrong with this sample, potentially, because this is too high. See, these were 43 to 45. So this is higher. But remember that these are all, now we're looking at only people who took exam 2. And this year anyway, the people who took exam 2 are almost exclusively people who had gotten into the on-ramps program. So it should be a bit higher because exam 1 was a huge chunk of what decided if you got in the on-ramps program. So it would be higher than the whole average. The other thing is, if you look at these two, so what we did is we took all these differences and we found their average right there. But that happens to be the same as x1 bar minus x2 bar. So I just kind of want to make the point that that is the same. So when we're doing the hypothesis testing on 2 independent samples, we find the average of the first and the average of the second, and we subtract. And in the dependent samples, we find the differences first and then average. So we could do it either way because everything in an average and a difference is addition and subtraction, and that's all commutative. If you have the same n. So if these had the same size n, we could have found differences and done it that way too. We wouldn't care about the differences because these aren't paired. So more specifically, I guess more usefully, in this situation you can find the averages and subtract, but you do need the list of the differences anyway to find the standard deviation. So let me show you, I guess, let me make this argument for why it's the same. Okay, so let's say that I have a list that's A1 through AN, and then I have their partners B1 through BN. A bar would be A1 plus A2 plus A3 and so forth down to AN over N. B bar, same deal but B's. Right? And we have the same N. So if I subtract these, that equals A1 plus A2 plus AN minus B1 minus B2 minus all over N, because I already have this common denominator, right? So this, if I wanted, I could just reorder things, right? I could just say A1 minus B1 plus A2 minus B2 plus down to AN minus BN. So all I did was move each of these over into their slot. And then I can put parentheses around these if I want. I don't have to do that to show this anyway, but I can. So that equals now D1 plus D2 plus down to DN. Okay, this is D1 plus D2 plus, where D is the difference between the partners, right? A1 minus B1, there it is. So this is the same. A bar minus B bar is the same as D bar, where D is the differences between the partners A and B. So x1 bar minus x2 bar is equal to D bar. These are the same. You couldn't do it this way if you had different sizes in lists, right? Okay, so back to this now. I'm going to just pretend I don't see these. Oops. These don't matter anymore. Okay, so I'm just looking at this. So I have a mean, and I have a standard deviation, and I have a size. I didn't ever do my degrees of freedom here. So my degrees of freedom here were 8 minus 1, which is 7. And my degrees of freedom here are 10 minus 1, from which I get my t, going back to my t chart. So we're still using 0.05 and we're still using two-tailed, so we're still in this column, but now I'm at 9, 2.262. And remember, oh, no, that's T critical. Okay. T critical is 2.262. My standard error. So this is back to our normal thing. So all it is the standard deviation divided by square root n. Okay, so we have an SE of 3.9. And so our difference is 6.5. So this would be, it's delta minus, it's D bar. Okay. So we're looking at D bar minus delta over SE, right, for D bar. But this we expect to be 0. Unless it's an unusual situation, we expect no change. So this is just going to end up being D bar, just like it previously ended up just being this guy, because we're always subtracting 0. So it's just this guy divided by the SE, and I'll just, okay, so I was dividing by the SE here, and I get 1.6624. So even though this group of people increased on average by 6.5 points, we would actually determine that there has been no change because 1.6624 is within the safe region. Because now our unsafe regions are 2.262, 2.262. Oh, my pen was upside down. Okay. So now we have 2.262 minus 2.262. So we're not right in the middle anymore. We're at 1.66, something like this, right? I guess a little closer like that. But it's still in the safe region, it's not in the red. So we would not reject the null hypothesis. If we looked at more of a sample, that might be different. I think maybe your scores, maybe they increased because of learning how the test works, or not writing up the extra explanations, or maybe that only canceled out the fact that the topics were harder. I don't know. But according to our statistics, we would say that there was no legitimate change between exam 1 and exam 2. Okay, so this is the end of my very, very lengthy video on 2 sample tests. And you can put in, well, I'll do a separate video for the calculator. How about that? And you have, I'll post the videos that the UT people made about the RStudio